Hello and welcome to the first video lesson in a long time. This will be short and quick and no math, so not as painful. So today we're going to talk about the speed of gases and what determines how fast gases can move, and then what factors affect their speed. So what's true is gases at the same temperature, so if two gases are, say, at like 100 Kelvin, they have the same kinetic energy. Okay? So if you have a gas of N2 and that is at 300 K, and a gas of O2 or oxygen and nitrogen, and they're both at 300 K, they will have the same kinetic energy. Sorry, I just got distracted by something. So again, if you have N2 and O2, if they are both at the same temperature, they'll have the same kinetic energy. Okay? But the question is, are the molecules moving at the same speed? And the answer is no. Okay? So the formula for kinetic energy, which is actually on your formula sheet, which you won't have to use any math, they usually don't ask you to do math with this formula, is the kinetic energy of anything, or in this case the kinetic energy of gases, is 1/2 the mass times the velocity squared. Okay? So, if two gases are at the same temp, they have the same kinetic energy. So same temp, same kinetic energy, okay? But because the lighter gases have a smaller molar mass, if this number is smaller, they must be moving faster, okay, to make up for the fact that they have a lower mass. If you remember in class, Mac asked, well, wouldn't heavier gases hit the wall with greater energy? Well, they're hitting the wall with the same amount of energy, and my pen is not working, which is annoying. Pointer options pen. So they'll hit the wall with the same amount of kinetic energy, because one will have more mass, the heavier one will have more mass, but less speed, and the lighter one will have lighter mass, but more speed. So the point here is that if you have two molecules, well, let's say in our previous example, okay, so let's say you have N2 gas and O2 gas at the same temperature. Since the H2 gas is lighter, this one weighs 28, this one weighs 32 grams per mole. Okay, the N2 gas will be moving faster because it's lighter than oxygen, but it will have the same kinetic energy because mass is part of the kinetic energy formula. So it will hit the wall of the container with the same force, because the kinetic energy is the same, because oxygen has more mass but less speed, and nitrogen gas has less mass but more speed. So the bottom line is that gases at the same temperature that have low molar masses move faster than gases that have higher molar masses. So if we take a look at this check for understanding, so if we have two gases, helium, I always hate that when that happens, so let me get my pen out. So we have helium and we have carbon dioxide, and they're stored at the same temperature. The question is, which one will be moving at a faster speed? So if you look at helium has a molar mass of about 4 grams per mole. And carbon dioxide has a mass of, I think, 44 grams per mole, if you add all the things together about. So since they're at the same temperature, and He is much lighter, it will be moving faster. Now again, they're going to hit the wall with the same amount of pressure because they have the same kinetic energy, because carbon dioxide is much heavier, but He will be moving faster because it's lighter. So here, another check for understanding. It says here, select the gas that has an average speed closest to Ne. All the gases are at the same temp and pressure. So you want to find the gas that has the closest molar mass to Ne. And the molar mass of Ne, if we're looking, and I need a periodic table. So the molar, I'm just going to round them and make them to the nearest whole number for this case, since it is multiple choice. So the molar mass of Ne is about 20. The molar mass of H2 is about 2. The molar mass of this is 4. The molar mass of water is 18. And the molar mass of carbon dioxide, we said, was 44. and the molar mass of is 32. So the one that would have the closest average speed if they were at the same temperature would be water, because it has the closest molar mass to neon in that case. So now we're going to talk about two new words. Effusion, which is the escape of a gas through a tiny hole in a container. So if there was a hole in the container, like let's say, how fast would the gas move? And diffusion, which is the spread of substances throughout a space, or if you opened a container. So you had a container with it had a barrier. So let's say there's a barrier right here. Right? Effusion is like there's a small hole. How fast the particles can go through the small hole. Diffusion would be if you remove the sort of barrier completely, how they would spread or they would diffuse into the empty space. So luckily here, we do not need to do any math, okay? So this is the equation, but they don't actually ask the math part of this equation. They just ask you to understand the concept, okay? So Graham's law of effusion, and remember effusion is how fast particles will move through a hole in a container, says that the rates of two gases are inversely proportional to the square roots of their molar masses. So basically what that means and what you need to know is that molecules with smaller molar masses will effuse or be able to get through the hole faster and be on the other side faster than those that have heavier molar masses. So helium has a molar mass of 4, and I don't know this molar mass, so 12 is 24, plus another 4 is 28, and then 28 plus 16, doesn't really matter, but 28 plus 16 is 44. So if you have the same amount of gas particles of helium in this side and the same amount of ethylene oxide on this side, and you let them effuse for the same amount of time, because the molar mass of helium is so much lighter, there'd be many, many more particles that have gotten through the hole than the number of particles that have gotten through the hole for ethylene oxide in the same amount of time, because it has a much heavier molar mass and moves much slower. Alright, so this is the last part of this lesson. And last year, 2 years ago, when I taught this topic, this curve caused a problem. And it's actually going to come back later in the course in one of the units. And this is called the Boltzmann distribution curve. And it shows the probability, okay, of gases moving at two different temperatures. So if you remember, we said that temperature is a measure of the average... Oh, the pen again went away. I love when that happens. So we said here, pointer options, pen, that temperature is the average kinetic energy of the particles. Okay. So here we have, if you look at this graph, which is called the Boltzmann distribution curve, on the x-axis we have speed, and really on the y-axis we have the number of particles. To simplify that thing, it really says number of particles. Well, it's really the probability that the particles will be moving at that speed. So we have a graph at a temperature of 80 Kelvin. And how is it different than the graph at a temperature of 300 Kelvin? Okay, well, we see, first of all, the peak for the gas that has a higher temperature occurs at a higher speed. And that makes sense, right? Because we said when particles have a higher temperature, they move more quickly. So the peak here, there are a lot of gases, or the peak of is where it peaks is at a higher speed. But there are less particles at their speed. There's more of a spread of speeds. Not all the particles are moving at a temperature or a speed of, let's say, like 410 meters per second. While that's the top speed, when the temperature gets higher, the graph shifts to the right, so it becomes flatter, but the peak moves over. So let's just summarize this again. Okay, so if you were drawing, so this is speed, right? and this is the number of particles, and these are gases at 2 different temperatures. So let's say we have, helium gas at 80 degrees Celsius and helium gas at 300 degrees Kelvin. Sorry, 80 degrees Kelvin and 300 degrees Kelvin. As the temperature rises, the graph shifts to the right, so the peak is at a higher temperature, but there's more spread. So if you were in AP Bio, you would say the standard deviation here is greater. There's a greater spread. Whereas at lower temperatures, while the hump is at a lower speed, there's less spread of speeds, or of possible speeds. So gases at higher speeds have a hump that's at a higher speed, but the hump is not as high, and there's more speeds available. Not all the particles are moving at 410. Some are moving at a bigger range of speeds. So I apologize for that weird transition. I had an interruption. I'm going to redo this slide. So this is a check for understanding. So we have, this graph shows helium and neon at the same temperature, and it wants to know which graph represents helium. So we remember speed, which is on the x-axis. Let's say we're numbering this 1 meter per second to 100 meters per second. The range doesn't really matter. Speed is affected by the mass of the particles, or the molar mass. So helium has a molar mass of 4, and neon has a molar mass of 20 about, I think. Yep. So from that, we know that helium, if they're at the same temperature, would be moving faster. So this one would be moving faster, and this one would be moving slower. And we just learned that when gases are moving faster, the peak shifts to the right, and the hump is at a higher speed. This is at a higher speed, but the hump is lower. So this gas is helium. Oh, I always hate when that happens. This gas is helium because it's moving at a greater speed. And remember, we said when the gases are moving at a greater speed, the graph shifts to the right, so the greater average speed is higher, but the hump is not as high. And then this one, which is the slower moving gas, has a bigger hump, but the greatest average speed is at a lower speed. So this here is neon. So again, the point is, okay, slower gases move faster. And if you look at this Boltzmann distribution, okay, when a gas is moving faster than another gas, its peak is, or the highest average speed is higher, like it's more over on the x-axis, but the peak is not as high. There's not as many molecules moving at the greatest average speed. So there's a more spread. So there are guided questions to answer, and I will see you guys on Thursday.